the previous lecture we were discussing about the thin film equation to be derived from all the boundary conditions and governing equations under thin film assumption. Now, the equation that we have derived is quite an involved one, and we need to actually appreciate the method of solving this problem, and to do that we will choose a very simple physical problem and try to analyze the method using that. So, the example that we will be talking about gravitational spreading of a cylindrical drop. So, let us say that you have a drop like this, which has a large length perpendicular to the plane. So, that basically this two dimensional description will give the complete picture of its spreading phenomenon. So, it is there on a surface, eventually this drop, because of gravity, simply by gravity, gravity is acting in this direction, it spreads like this, and at some point of time. So, if you call this as x and the height as h, this local height h is a function of x and time. At some point of time, you will have a situation when this entire droplet is spread on the surface, in a sense that this maximum height is 0, and when this maximum height is 0, we say that the spreading process is complete. So, one of our great interests will be what will be the spreading time, or in general how will this h depend on x and time. The first question that we will ask ourselves, is it really a thin film problem? This is the first question that we would ask. So, in the thin film problem, the basic premise is the existence of a small parameter epsilon, which is h naught by L c. This is the characteristic thickness of the film or the maximum thickness of the film, and this is the length scale along the x or axial direction. This has to be small. In this case, when the drop starts spreading, this maximum height and the axial length scales are comparable. Only when the spreading is towards the end of its journey, around that time you will have the h much less as compared to L. So, only during that time you can apply the thin film theory for solving the film thickness. So, again I am repeating, at the early stages you cannot use the thin film, because at the early stages the height of the droplet is significant as compared to its footprint. only when it during spreading towards the end of the spreading its thickness becomes negligible as compared to its footprint on the surface, then only you can say that yes, thin film can be applied. So, end stage. So, we will solve this problem from the first principles by using this set of equations, which I have written in the previous lecture in the board, and I have not yet erased because I had it in mind that I will use this to solve this particular problem. So, what are the simplifications that we can do here? First of all, how to solve a problem in thin film dynamics. We have a thin film equation and we know how to derive the thin film equation from the first principles, but what appears to be missing here, whatever is written, what is clearly missing is what is UC, that is missing. So, as I told you that this mathematics of solving a thin film problem is very structured. What is not so structured is the following. What is not so structured is to identify the correct physics based on which you will get this UC. In this case it is quite obvious. So, first of all, in this case there is no body force in the x momentum equation, because entire body force is vertically downwards, which is due to gravity. So, I am crossing this term. What will be f dash y? Minus rho g sin theta. In this case theta is 90 degree, so minus rho g. Most importantly, see, we have discussed that out of various variables which can define the velocity scale, if x momentum body force is important, that will define the velocity scale. If y momentum body force is important, then that will define the velocity scale. If the surface tension tangential gradient is important, that will define the velocity scale. If the Laplace pressure is important, then the coefficient of the curvature term will decide the velocity scale. If the disjoining pressure is important, then this will define the velocity scale. In this case, what is important? In this case, the y momentum equation is important. Because the y momentum equation is important, so this term, so let me do it. So this is rho g. So this term will dictate the UC. So this is of the order of 1, because this is scaled non dimensionalized with proper scale. So this derivative is of the order of 1. Therefore this total term must be also of the order of 1, so that these two are competitive. So if that be the case, you have UC. So if this total is of the order of 1, UC is of the order of epsilon cube LC square by epsilon cube LC square rho g by mu, right. So this is the first, and I believe this is the most important step, because remaining step is algebra, calculus, everything, but this step is the physics and you have to be very, very careful about it. Now based on this velocity scale, you can estimate the capillary number. Capillary number, viscous force by surface tension force, mu uc by sigma. So, mu uc by sigma is epsilon cube LC square So, you divide by LC both numerator and denominator. So, LC rho g okay. So, this is nothing but the capillary pressure and this is the pressure due to the hydrostatic effect or the gravity, right. So, this is essentially the gravity force by surface tension force and this is called as bond number. When there is a gravitational spreading of the drop, that means gravity is the dominating force. When gravity is the dominating force, you can assume that the bond number is large. You may argue that the curvature effect is also very important, but not at the very end stage of spreading. So, at the very beginning of spreading, this is also very critical. Gravity is important, curvature effect is equally important. The droplet eventually flattens down and the curvature effect becomes less and less. So, towards the end you will find that this effect is much less as compared to this, and that means the physics of the problem, the regime where we are working on is bond number much less than 1, much greater than 1. So, epsilon cube by capillary number, this is 1 by bond number, this is much less than 1, right. Look at the boundary condition where epsilon cube by capillary number appears and it is the curvature term. So, this epsilon cube much by capillary number much less than 1, these are all non-dimensionalized. It shows that, and this is the non-dimensional surface tension. So, this is also of the order of 1. This shows that this entire curvature term can be neglected in the normal force balance boundary condition. So, this shows that from normal force balance you have Ps minus P0 is equal to Pex. The curvature term is negligible. Now, this is a key question, because I am illustrating it in a elementary class work where it is not to demonstrate you research issues. I am forcefully neglecting it to simplify the algebra with an understanding that yes, this is negligible to a large extent, but in the finishing stage the droplet almost completely has its footprint on the surface, then the film thickness is so thin that van der Waals forces can actually become very important. So, at not always at the end stage, but at the super end stage, that is almost the droplet spreading is complete, then this effect is important. So, here we are neglecting this. So, if we neglect this, remember that we cannot neglect this always, but this is just a simplification that we are making. So, you will have Ps equal to P0. approximately equal to, but for all practical purposes we will consider it to be equal. Okay. Having said that, so this is number 1. Number 2 is, in this problem there is no tangential gradient of surface tension, that means this term is also 0. Okay. So, with these two considerations, with which equation we will start? We will start with the y momentum equation and integrate it over the film thickness. So, y momentum okay. And this is of the order of 1, right, this entire thing is of the order of 1. So, if you integrate it with respect to y, p is equal to minus y the boundary condition it as y equal to h, p equal to ps. So, ps is equal to p naught, right. So, p equal to ps and ps is equal to p naught from the normal force balance. So, p equal to p naught plus h minus y. For y momentum equation you require for x momentum equation you require minus del p del x. So, del p del x, p naught is a constant, its derivative is 0, it will be del h del x, right. So, now we have got this as del h del x, we will now integrate the x momentum equation twice. Just integrate twice, u is equal to del h del x, sorry, del u del y, we will do it in 2 steps. First boundary condition. So, what we have used so far? We have used the x momentum yes, y momentum yes, tangential force balance not yet, no slip not yet, normal force balance we have used. So, we will use the two boundary conditions at y equal to 0 u equal to 0 and at y equal to h del u del y equal to 0. At y equal to 0 u equal to 0, that means C3 equal to 0. At y equal to h del u del y equal to 0, that means C2 is equal to minus del h del x into h. So, you at y equal to h, at y equal to h you have del u del y equal to 0. So, C2 is minus h into del h del x, right. So, you have u equal to del h del x into y square by 2 minus y h. This is our velocity profile. So, next step is integrating the continuity equation. So, if you integrate the continuity equation and use the Leibniz rule, I am not going to do it again because we have already done it in the previous thing, and use Leibniz rule plus kinematic boundary condition. What you will get? Del h del t just check once whether del del x of x, right. This we derived in the previous lecture. So, del h del t I have written del x twice. So, this will be h cube by 6 and this will be minus h cube by 2. So, h cube by 6 minus h cube by 2. So, this will be minus h cube by 3. Right. So, this is all right. So, now I am in a position to delete the entire thing which is there in the left side of the board, because I have used all equations. Now, this equation is a partial differential equation, right, but this can be transformed into an ordinary differential equation by virtue of a transformation called as stretching transformation. Such a stretching transformation is available or is permissible if the method, if the physics of the problem is self similar with respect to x and time. So, in this case we define h is equal to t to the power alpha into a function of eta, where eta is defined as so you can see that we form a similarity variable, and what we try to do is we form the similarity variable by combining x and t, because the at a given x the height is dependent on t. So, if you freeze x and t together, you may come up with a unique similarity variable that can include the solution. So, now we will do the algebra here. Question is that with this has to transform to a ODE, ordinary differential equation. If it does not, that means similarity solution does not exist. So, del H del T so this is a function of t directly, this is a function of t implicitly, because eta is a function of t. So, df d eta, this is a function of eta only, into del eta del t. So, a x minus beta t to the power this. There is a t to the power alpha, right. A x by t to the power beta is eta. So, and this t to the power alpha minus 1 makes it t to the power alpha minus 1. So, t to the power alpha minus 1 alpha f minus beta eta f dash, okay. So, we have calculated this term, then we have to calculate this term, del h del x, this is more straightforward to calculate because this is only function of x, df d eta del eta del x h cube by 3. So, h cube is t to the power 3 alpha f cube by 3 del x of this is d d eta of this into del eta del x. So, d d eta of this is d d eta of f cube f dash, I will write the remaining coefficients subsequently, into del eta del x is a by t to the power beta. So, a square by 3 t to the power 3 alpha plus alpha 4 alpha minus beta minus another beta. So, 4 alpha minus 2 beta. So, this equation boils down to t to the power t to the power alpha minus 1, right hand side also there is okay t to the power alpha minus 1, right hand side is t to the power 4 alpha minus 2 beta. So, t to the power alpha minus 1, where is it, yes, alpha minus beta, not sorry, that we will do it later, alpha f minus beta eta f dash, right, is equal to t to the power 4 alpha minus 2 beta into a square by 3 into d d eta of f cube f dash, right. Hopefully there is no problem with plus minus sign, right. I believe there is no problem with plus minus sign. Okay. Now the most important mathematical step, to convert this equation to ODE, you must have only the dependent variable as f as a function of eta, there should not be any presence of t. So, if there is no presence of t, you must have alpha minus 1 is equal to 4 alpha minus 2 beta. Okay. But this does not tell you what is alpha and what is beta. We have not used another very important physical constraint, that is, whenever the droplet is spreading, in the absence of evaporation, what is remaining conserved is its volume. So, the constraint is volume conservation. If you are modeling evaporation, you can put a modified volume constraint taking into account the evaporation flux, but otherwise the volume conservation so volume conservation if L is the length of the footprint of the droplet, which is a function of time, this is constant, and this constant you can scale arbitrarily. So, h is, what is h? H is equal to t to the power alpha into f, and f is equal to and eta is equal to a x by t to the power beta, right. So, dx from here is t to the power beta a d eta. So, this is t to the power alpha f a t to the power beta d eta yes, yes, dx is this is 1 by a. So, this is 1 by a. Okay. So, you have, so eta, let us say when x is equal to L, which is the length of the drop, the eta is correspondingly eta naught. So, so this is the droplet, if this is L, the corresponding name of the eta variable is eta naught. So, now this has to be also independent of t, right, volume has to be independent of t, that means alpha plus beta equal to 0, and as a consequence integral f d eta is equal to A into C. Because these are scaled similarity variables, you can normalize and choose C equal to 1. So, alpha plus beta equal to 0 means beta is minus alpha. So, 4 alpha plus 2 alpha 6 alpha minus alpha. So, 5 alpha is equal to minus 1, this means alpha is equal to minus 1 by 5. So, if alpha is minus 1 by 5, so you can clearly see now we have got how H depends on time. So, we have got one answer, we have not yet got the solution of the equation. So, when alpha is equal to minus beta, we have alpha that is minus 1 by 5 f plus eta f dash okay. So, then you can choose a square is equal to 3 by 5, right. If you choose a square is equal to 3 by 5, then you see all these 3, 5 all these things cancel. So, this is choose, all these are scaling coefficients. So, these scaling coefficients can be arbitrary. So, then you are left with f plus f dash eta is equal to minus d d eta of f cube f dash, right. This is nothing but d d eta of f into eta. So, now if you integrate you will get f eta is equal to minus f cube f dash plus a constant k. So, what are the boundary conditions? At x equal to 0 you have del h del x equal to 0, this is because the droplet is symmetric with respect to the y axis. So, that means at eta is equal to 0 you have f dash is equal to 0, right. That means k equal to 0. Okay. So, you have f cube df d eta is equal to minus f eta, right. So, f square df is minus eta d eta. Now, you integrate it, okay, we will integrate and put the boundary condition. This is f cube by 3 is equal to minus eta square by 2 plus k2. What is the next condition? At eta equal to eta naught, which is the footprint, the height is 0, that is f equal to 0. So, at eta equal to eta naught you have f equal to 0. So, k2 is equal to eta naught square by 2. So, we get the solution f cube by 3 is equal to eta naught square minus eta square by 2. But still you do not know what is eta naught, but what you know is integral f d eta from 0 to eta naught is equal to a, right. So, integral f d eta from 0 to eta naught is equal to a, which is square root of 3 by 5. So, this f is okay. So, this if you do this integration is not analytically possible, but you can do it numerically. A trick is substitute eta equal to eta naught sin theta, and then if you do this numerical integration you will get a value of eta naught, because everything else is known. So, let me look into my notes and tell you what is the value of eta naught, so that you can do this numerical integration by yourself. Eta naught is equal to 2.23. By numerically integrating this integration you will get a solution for eta naught. So, now you have eta is equal to ax by t to the power beta, right. So, when you have eta naught, this is L. So, and beta is minus alpha, huh? Yes. So, this one. So, that means from this equation now you can get the length of the droplet. So, this is 2.23 as a function of time and other parameters. Okay. A of course, we have already assigned a value of a square root of 3 by 5. So, this gives the final solution that given a particular length of the droplet, how that length of the droplet will evolve, given an initial length, eventually how that length of the droplet will evolve as a function of time. We have come to the end of this series of lectures on thin film, and I hope that the last example that I have provided through this entire lecture is quite comprehensive, and it will give you a general idea of how to solve the most general problems with, say, additional field effects, electric field, magnetic field, instead of no slip boundary condition, slip boundary condition. All these research problems you can tackle under this common framework. Thank you very much.